Okay, so you know that like little itch in the back of your mind? The one that like always makes you want to think about the like real fundamentals of things,
Hmm.
especially like when it comes to how we reason, the very structure of logic itself. It makes you ask a big question, right? Like how much do different elements, different ideas truly rely on each other?
Right, like how does the validity or the truth of one concept get completely tied up with others?
Well, if you're fascinated by that, those kind of dependencies and knowing you, a philosophical mind, I bet you're going to love this. This deep dive, it's designed specifically for that part of you that loves to pick apart the logical underpinnings of, well, everything. We're going to jump headfirst into dependence logic. It's a really cool extension of standard logic, and you can think of it as like a specialized toolkit for formally examining, like articulating that very notion of reliance, how the value or state of one thing is determined by others.
Exactly. It takes this intuitive understanding that we have of dependency and gives it a precise and rigorous logical framework.
And to make sure we're on solid ground here, our whole conversation today is going to be based on the entry on dependence logic from the Stanford Encyclopedia of Philosophy, the one you sent over. It's a super thorough and respected source, so we know we're working with the core ideas in a reliable way.
Yeah, for sure. It's a great overview. It really traces the development of this whole area from its basic principles to its different variations and even real-world applications.
Yeah, it's amazing. So, a goal today is pretty direct, but hopefully it'll be really insightful for your philosophical perspective on logic, the idea of dependency, and even how we grasp information. We want to give you a new way to look at these basic concepts, like a new lens through which to analyze them. So, how about we just unpack this? Where do we even start to see these hints of dependency, even within like the logic we're already familiar with?
Well, I think that's a great place to start. Even in standard first-order logic, the idea of dependency is actually already there. It just works more implicitly, kind of in the background. Think about the way we use nested quantifiers and the whole concept of their scope.
Scope, yeah. That's a concept that can sometimes feel a bit abstract. Can you give us like a nice concrete example to illustrate that?
Sure, let's take the classic statement. Every boy loves some girl that loves some other boy. We can express this in first-order logic as, for all x, if x is a boy, then there exists a y such that y is a girl, and x loves y, and there exists a z such that z is a boy, and x is not equal to z, and y loves z.
All right, I can follow that, yeah. It's a chain of these quantifiers and variables all nested within each other. So where's the hidden dependency in all that?
Well, the nesting itself is the key. Notice how the existential quantifier for the girl, y, it falls within the reach, the scope, of the universal quantifier for the boy, x. What this means is that the choice of the girl can depend on which boy we're talking about. Right, different boys might love different girls. And then the existential quantifier for the second boy, z, that's within the scope of both x and y. So who that second boy is, it can be influenced not just by the first boy, but also by the specific girl he loves.
Ah, so the scope sets up this kind of cascading effect of dependency. Like the girl exists, logically speaking, only because of the boy. And then that second boy's existence depends on both the first boy and the girl. It's like a logical chain reaction, right?
Mm.
But the crucial point here is that the structure of standard logic kind of forces these relationships into a specific order. And like we'll see, that limits the types of dependencies we can express.
Precisely. The Stanford Encyclopedia entry even points out other helpful examples, like the formal difference between continuity and uniform continuity in math and analysis. The order of those quantifiers and how we write them logically determines whether this thing called delta can depend on both epsilon and a specific x, or if it's got to depend solely on epsilon.
I see, that makes sense. And they even talk about that didictode redistinction in intentional logic, like whether a modal property applies to the proposition itself or to a thing mentioned within it. Again, it seems to come down to the scope of that modal operator and what dependencies it implies. So standard logic does capture this idea of dependency, at least indirectly. What's the problem then? Why do we need to go beyond it?
That's where it gets super interesting. The main problem is that standard first-order logic, in how it represents dependency, is limited by the linear way quantifier scopes work. They have to be in order. And this means that the dependency patterns we can write directly are always transitive.
Transitive, meaning if A depends on B and B depends on C, then A has to depend on C as well, like an unbroken chain of command.
Exactly. And the source uses a slight but important tweak to our boy and girl example to show this. Imagine this. Every boy loves some girl that loves some other boy, and that second boy can be chosen totally independent of the first boy.
Okay, it's subtle, but I see the change. So every boy, there's a girl he loves. She, in turn, loves some other boy, but, and this is key, the identity of that second boy isn't tied to the first boy at all. It's just based on the girl.
Precisely. Maybe two different boys are both in love with the same girl, right? And that girl loves the same second boy, regardless of who the first boy was. Our original first-order logic way of writing this, it just hits a wall if we want to express this directly. Because if C, the second boy, is within the scope of Y, the girl, and Y is within the scope of X, the first boy, then Z is automatically also within the scope of X. We're stuck with that transitive dependency.
I see the restriction. We're trying to say Y depends on X and Z depends on Y, but Z doesn't depend on X. Standard logic, just the way it's built, doesn't let us say that kind of non-transitive dependency directly. The article mentions that you could kind of hack it by using higher order quantification, basically quantifying over functions.
Yeah, exactly. And equation 2 in the text shows how that works. You bring in an existential quantifier over a function, let's call it f, that takes the girl as input and spits out the second boy as output. He gets the job done, but it pushes us outside of standard first-order logic, right? We're explicitly quantifying over functions now.
Which feels like a pretty big jump in complexity for what seems like a small change in the dependency. So is that where dependence logic comes in, to handle those non-transitive situations more directly?
That's exactly why it was created. Dependence logic adds this new fundamental building block. It's an atomic formula called a dependence atom, and it looks like this. And what this atom states is that the value of the variable y functionally depends on the values of the variables through deset 1. Basically, once you know y, too.
Okay, that sounds a lot more straightforward, a more focused way to say that one thing is determined by others. Now, the text contrasts this with things like branching quantifier logic and independence-friendly logic, saying that those actually modify the structure of quantification itself.
That's right. Logics like Henkin's branching quantifier logic or independence-friendly logic, they can express similar dependencies, but they do it by changing how quantifiers themselves work and interact. Dependence logic keeps the familiar quantifiers we're used to, but adds these explicit statements about the relationships between variables.
Interesting. So how does that modified boy and girl situation, the one with the independent second boy, how does that look in dependence logic?
It's actually quite elegant. Equation 5 in the text shows it. For all x exists z, y, z, land, y, land loves, right x, y, z. The important part is the dependence atom. That's how we directly formalize the idea that the second boy only depends on the girl, not the first boy.
Yeah.
That looks much cleaner. It isolates that specific dependency we want. The text mentions that the truth conditions of this dependence logic formula line up with what you get using higher order quantification or those other fancier logic systems, at least when we're talking about full sentences.
Yeah, and that's important. For complete sentences, formulas without any free variables, dependence logic, existential second-order logic, and independence-friendly logic, they all have the same expressive power. They can define the same kinds of model classes, the same logical structures that satisfy them. But how they do it and what happens when you have formulas with free variables, that's where they differ. Plus, each of these logic systems can be extended in very different ways, which leads to a really diverse range of logics of dependence and independence.
Fascinating. So dependence logic gives us the syntax, the words, to talk about dependency directly. But the source keeps mentioning team semantics. What's that all about?
It's the foundation of how we understand meaning in dependence logic. It's like a generalization of the typical Tarski semantics we use for first-order logic. The main difference is that instead of looking at truth in terms of one single assignment of values to variables, team semantics uses sets of variable assignments. We call these sets teams.
Teams, like a collection of different possible assignments, a bunch of scenarios. The text even compares it to the idea of belief sets. It's like, we're not just considering one fixed reality, but many ways the world could be. Why is this helpful when we're thinking about dependency?
You got it. You can think of a team as representing a set of possible situations, or like you said, all the assignments an agent thinks are possible. And a team, we call it, satisfies a formula, let's say, if and only if, holds true across all the possibilities within that team. This shift is what lets us capture dependencies that hold across a range of possibilities, not just within one fixed interpretation.
Wow, so it's a pretty big shift in perspective. Instead of a single snapshot, we're looking at a whole bunch of them at once. How does this team-based view then change how we interpret those logical formulas, especially the dependence atoms?
So for the dependence atom, Laruskart by 1 pi 1 pi 1 holds if and only if for any two assignments, call them S1 and X2, that are in team X. If those two assignments give the same values to 1, then they have to assign the same value to y as well.
Let me make sure I got that. We have a team with multiple scenarios, and in every scenario we're the same, then y also has to be the same. That's when the dependence atom is true for that team. It's like saying that within all our possible scenarios, y is totally predictable based on through 1 through xn.
You got it perfectly. The example they use about nationality, test scores, and acceptance makes this really clear. If equated by 2 is true, where is the score and y is acceptance, it means that anyone who gets the same score in all the possibilities in our team gets the same acceptance decision. It doesn't matter what their nationality is or any other factor in those assignments. There's also this thing called constancy atoms, written as equated. That's just a special case where the variable has to have the same value in all the assignments in the team.
Okay, so that makes it really clear how dependence and constancy get more, well, complex when we're dealing with a set of possibilities instead of just one fixed world. What about the other logical connectives like conjunction, disjunction, and quantification? How do those work in this team semantics world?
Okay, so for basic first-order literals, like when we say excellent, and then for conjunctions written as fetal socks, the rules are pretty intuitive. A team satisfies a literal if and only if every assignment and satisfies it in the usual Tarski way. And a team satisfies a conjunction if and only if satisfies both and psi.
Okay, so that's familiar. It's like those conditions have to be met across all the possibilities we're thinking about.
Right, but disjunction, that's where it gets more interesting. The rule for disjunction, written as file, is X models find psi if and only if the team can be split into two subteams. Let's call them Y and Z. So X is just Y and Z, and Y satisfies. And remember, Y and Z don't have to be completely separate. They can overlap.
So to say a disjunction is true within a team of possibilities, every possibility in that team has to belong to at least one of two sets. Either the set where the first disjunct holds, or the set where the second one holds. It's a lot like belief states. If I think either phi were true, then all my possible worlds should be divisible into those where phi holds and those where holds.
You're exactly right. And the text points out something that might not be obvious at first. Disjunction, independence logic, isn't idempotent. That means equared XY is not logically the same as just saying once. The disjunction is actually a stronger condition.
That's really interesting. Why does that happen? Why isn't it idempotent?
It's because equared X requires our team X to be splittable into two teams, Y, and those could be the same as self,
Right.
where Y depends on X within team Y, and Y also depends on within team. This doesn't actually guarantee that Y depends on in the original team, in the same way as single would. The combination of two things that are functions isn't always a function in the same way, you see. So it's like knowing something is true under one set of circumstances and knowing it's true under another set, even if they overlap, isn't the same as knowing it's true under a single overarching set of circumstances.
Oh, wow. That's a subtle but crucial distinction. Okay, what about the quantifiers? How do for all, written as for all, and there exists, written as exists, work within this team setup?
For universal quantification, so X models for all V psi, that's true if and only if XMV models V psi. XMV is a new team we build by taking every single assignment in the original X and expanding it to include all the possible values for our model. So basically, for each scenario in our current team, we branch out and consider all the possible values for V's.
Okay, so to check if for all V is true in our starting team, we have to make each scenario in X cover all possible values for V. This gives us a bigger, more complete team, and then we see if EK holds across that whole expanded team.
Precisely. And for existential quantification, X models exists, VPAI, holds if and only if there's some team, we'll call it Y, defined over the same variables as X plus the variable V, such that when we project Y back down to the original variables of X, we basically forget about V in each assignment, and this is written as Y slash V so backslash V so X slash V, and this new team Y has to satisfy the formula. It's like saying that D psi is true if we can find a way to assign a value to V for each assignment in X, maybe giving us multiple assignments in Y for each original one in X so that it becomes true in that resulting team Y.
So existential quantification is like finding a suitable witness for that quantified variable within a set of possibilities that matches our initial team when we ignore the quantified variable. This whole team semantics thing adds a lot of dynamics and subtleties to the logic. It's really different from standard Tarski semantics.
Yeah, definitely. And from these basic semantic rules, dependence logic gets three key properties: locality, downwards closure, and the empty set property. Locality just means that whether a team satisfies a formula only depends on the free variables that actually appear in that formula. Downwards closure says that if a team satisfies a formula, then any subset of, so any smaller team of possibilities, also satisfies that same formula. And the empty set property says that the empty team, the one with no assignments, well, it satisfies every formula independence logic. These are kind of like sanity checks for logics using team semantics. What would it mean if they didn't hold? Like, imagine if downwards closure wasn't true. A formula could be true when you consider a lot of possibilities, but false when you zoom in on a smaller set. That would be pretty weird, right?
Those sound like pretty important properties. They tell you how the logic behaves at a fundamental level. The text also talks about game theoretic semantics as another way to understand dependence logic. They compare it to how imperfect information games are used for IF logic. How does that perspective relate to this team semantics?
Right, so there's this game theoretic interpretation, and it's similar to the one for independence-friendly logic. A sentence, together with a model, defines a game between two players. And the truth of that sentence is linked to whether one player, usually called player zero, who's trying to show the sentence is true, has a winning strategy. The game is all about moving through the subformulas of the sentence. For disjunctions and existential quantifiers, player zero chooses which path to take or what value to use. For conjunctions and universal quantifiers, player one makes the choices. That's pretty standard for game theoretic semantics, yeah. Where do those dependence atoms come in? That's interesting. Dependence atoms don't actually say who wins or loses in a single play of the game, which ends when you reach a first-order literal and check its truth value against the current variable assignment. They set up a uniformity condition for what counts as a valid winning strategy for player zero. Player zero's strategy is only uniform if, whenever two different plays of the game end up at the same dependence atom with the same values for the dependent variables, then the value chosen for y must also be the same in both plays. This uniformity condition directly reflects that functional dependency. The value of y is fixed once you know through can. And the text emphasizes that this game theoretic semantics has been proven to be equivalent to team semantics.
Wow, so two different ways of looking at meaning and truth in dependence logic, and they end up being the same. That's pretty neat. Now let's talk about expressive power again. We talked about how dependence logic, when it comes to complete sentences, is equivalent to existential second-order logic. What does this connection tell us, especially from a philosophical point of view, about the nature of logical expression?
This is a big result, and it has some deep implications. It tells us that anything you can say in dependence logic, you can also say in the existential fragment of second-order logic, and they'll be true in the exact same models, and vice versa. Now, Fagin's theorem links existential second-order logic on finite models to the complexity class NPTE, which stands for non-deterministic polynomial time. So this means that if you have a dependence logic sentence, the set of finite models that satisfy it belongs to NPT. And the other way around, if you have some property of finite models that can be decided by an NPT algorithm, you can express that property with a sentence in dependence logic. This tells us, from a philosophical perspective, that dependence logic has a lot of power to describe structural properties of finite domains. It lines up with this complexity class that's often associated with problems that are hard to solve but easy to verify.
That's a deep connection to computational complexity. So dependence logic is strong in terms of what it can say about logical structures. It's as powerful as allowing us to say there exists some relation. The text also mentions that properties like compactness and the Löwenheim-Scullum theorem hold for dependence logic just like they do for first-order and full second-order logic.
Yeah, exactly. Those are important properties that describe how the logic works when we have sets of sentences and different sizes of models. Compactness means that if a set of dependence logic sentences doesn't have a model, then some finite subset of those sentences also won't have a model. The Löwenheim-Scullum theorem means that if a dependence logic sentence has an infinite model, then it also has models of every other infinite size. These are considered really good properties for a logical system to have.
But the source also points out that when we look at formulas with free variables, things aren't as simple.
That's true. When you have free variables, dependence logic corresponds to the downwards closed fragment of existential second-order logic. This means the sets of teams that can satisfy a dependence logic formula are always downwards closed. Remember, if a team satisfies the formula, any subteam, a subset of those assignments, also satisfies it. And these sets of teams are exactly the ones definable by a special type of existential second-order formula.
Downwards closure seems to be a really important feature of dependence logic. Now, the Stanford entry then talks about different variants of dependence logic. That sounds like where the basic ideas are extended and adapted.
Yeah, that's right. Researchers have explored what happens when you add different kinds of atomic formulas or logical connectives to the basic framework of first-order logic with team semantics. And this has led to a whole family of logics of dependence and independence.
Let's start with independence logic. Instead of dependence atoms that explicitly state reliance, independence logic uses independence atoms to assert a lack of connection. That sounds pretty interesting.
Independence logic introduces atomic formulas that look like this. Vec stop, vec y, which basically means that if you fix the values of the variables in vec, then the values of the variables in vec x and the values of the variables in vec y become statistically independent from each other within the team. So once you know, knowing the values of vec doesn't give you any more information about the values of vec and vice versa.
That sounds like a really powerful way to formally say that there's no relationship instead of saying that there is one. The example in the text about encrypted messages and decryption keys really illustrates that concept.
Exactly. And it turns out that independence logic is more expressive than dependence logic. For example, it doesn't have that downwards closure property that's so characteristic of dependence logic. Interestingly, you can express the dependence atom within independence logic as vec y. So even though it's still equivalent to existential second-order logic when it comes to complete sentences, in terms of formulas, independence logic can capture more properties of teams than dependence logic can. Okay, the next one on the list is inclusion logic with its inclusion atoms. What kinds of relationships are those meant to capture? Inclusion logic uses these atomic formulas that look like this. Vec x subsatec vec y. What that means is, for every combination of values that the variables in vec take within the team, there must be at least one assignment in that same team where the variables in vec y take on that exact same combination of values. This idea is closely related to inclusion dependencies, which are really important in database theory.
So it's about making sure that the set of possible values for one set of variables is fully contained within the set of possible values for another set of variables within our team.
Exactly. And unlike dependence and independence logic, inclusion logic, when we're talking about full sentences, is actually weaker than existential second-order logic. It's been shown to be equivalent to the positive fragment of greatest fixed point logic, and it can define exactly those properties that can be decided in polynomial time, or PTIE, on finite ordered models. Now, formula-wise, it doesn't have downwards closure, but it does have this closed by unions property. If a bunch of teams each satisfy an inclusion logic formula, then their union will also satisfy that formula. Its expressive power is also incomparable to dependence logic, being strictly weaker than independence logic.
They have team logic, which seems to take dependence logic and add a very basic logical operation.
Yeah. Negation. You got it. Team logic is like dependence logic, but with a regular negation operator, usually written as xdel not. It follows the usual rule. If and only if it's not the case that X models funge. This seems like a small change, but it has a huge effect. It makes team logic just as powerful as full second-order logic, both when defining classes of models and properties of teams themselves.
Wow, that's a big jump in expressive power. Just adding regular negation takes us to the level of full second-order logic. That really shows the power of this team semantics idea. The text also mentions intuitionistic dependence logic, which brings in an implication connective.
Right, intuitionistic dependence logic adds an implication connective, written as phi right RO psi, with this rule. X models phi right RO psi. If and only if for all subsets Y of X, if Y models phi, then Y models phuth. This implication is similar to what you see in Kripke semantics for intuitionistic logic, and it makes sense if you think about how beliefs are updated. But because it has this implicit second-order universal quantification in its semantics, it also makes the logic as powerful as full second-order logic. And it's interesting because even though it's more powerful, it keeps the downwards closure property.
So all these ways of extending dependence logic, adding independence atoms, inclusion atoms, negation, or intuitionistic implication, lead to logics with vastly different powers and properties. It's like a whole family of logics growing out of this idea of team semantics. The entry even mentions more specialized areas like generalized dependencies and connectives, propositional dependence logic, modal dependence logic, and even connections to temporal logic and quantum mechanics. It seems like this whole framework is incredibly versatile.
Absolutely. Researchers are still figuring out the limits of team semantics by introducing all sorts of generalized dependence atoms and connectives. They want to know when these additions keep desirable properties, like first-order expressivity, or when they play nicely with existing dependencies. Propositional dependence logic takes the core ideas of dependence and applies them to propositional logic, where dependence atoms link propositional variables. It's interesting because it turns out not to be more expressive than standard propositional logic, but it has a strong connection to inquisitive logic, which is used to study meaning, questions, and how information is shared. Modal dependence logic takes the ideas of dependence and applies them to modal logic, with the dependent atoms that work across possible worlds. And like you said, team semantics has even found uses in linear temporal logic for specifying something called hyperproperties, and even in quantum logic. In quantum logic, quantum teams can be used to model those strange quantum events that break Bell's inequalities, something that classical logic usually can't handle.
That's incredible. I had no idea this area of logic was so rich and connected to so many different fields. It goes from databases to belief representation and even the fundamentals of quantum mechanics. The last section of the entry talks about some of these applications of dependence logic in more detail.
Yeah, it shows just how important these logical concepts are, both in theory and in practice. The connection to databases is especially strong. Teams can be naturally seen as database relations, and the different dependence atoms correspond to database dependencies that we already use, like functional, multi-value, and inclusion dependencies. This has helped both areas, with insights from one being used in the other. The use of dependence logic in belief representation, particularly how it connects to inquisitive logic, gives us a formal way to think about information, asking questions, and how agents' beliefs change as they interact. Also, Arrow's impossibility theorem in social choice theory has been formalized using dependence and independence, which shows that these tools can be used to analyze important concepts in other fields. And the work on quantum team logic is opening up entirely new ways to think about the logical foundations of quantum mechanics. It might give us a more natural framework for understanding the weirdness of quantum phenomena.
So, to sum it all up, dependence logic is a powerful and formal way to describe how the value of one thing is determined by others. It goes beyond the limits of standard first-order logic by using this new concept of team semantics, where we look at truth across sets of possibilities, not just single assignments. This allows us to express non-transitive dependencies, which standard logic can't do easily, and it's created a whole bunch of related logics, each with its own strengths and connections to different fields.
Exactly. It gives philosophers new and sophisticated tools to analyze fundamental concepts like dependency, the flow of information, and even the nature of logical consequence. This is especially relevant when we're dealing with situations where there are multiple possibilities or where agents don't have complete information about the world.
It makes you think about how often we run into situations in philosophy and in life where dependencies aren't as simple and linear as standard logic might suggest. Maybe dependence logic can give us new and better ways to understand those complex relationships. It could be useful for thinking about free will, causality, or even the very nature of information itself.
That's a great point. The subtleties of team semantics and all these different dependence logics open up really exciting ways to investigate the foundations of logic and its ability to capture how we reason and understand the world.
For anyone who's curious about this, I definitely recommend checking out the Stanford Encyclopedia of Philosophy entry on dependence logic. It's really interesting, and it'll lead you to a lot of other fascinating areas in the field. Think about those old philosophical problems and how they might look different, how they might make more sense when you view them through the lens of dependence logic. It's a lot to think about.
Absolutely. What are the limits of standard logic when it comes to describing those often subtle and complex dependencies that we intuitively grasp? What can these new logical systems do to change our understanding of some of our most basic and debated concepts? These are the kinds of deep questions that studying dependence logic pushes us to ask.
Well, on that note, thank you so much for joining us today. And to all our listeners out there, keep those philosophical minds churning. Until next time.
Thanks for having me.